All right, class, we are now arriving at looking at inverse trigonometric functions. And so function has an inverse if and only if it is one-to-one. So this means that it passes the horizontal line test, therefore it has an inverse. So if we restrict a domain to certain intervals, the sine, cosine, tangent functions have inverse functions also. So for those of you who have taken algebra, college algebra, or currently taking college algebra, we know that a function is defined as a function as long as it passes the vertical line test. And an inverse exists if it passes a horizontal line test. So if we think of our trig functions, for instance, sine, right, let's come over here, let's think of our pattern for sine. So our pattern for sine is middle, high, middle, low, middle. Right, so we're going to come here, we're going to come up to our high here, we're going to come down to our low, and back to our middle. So it's going to look like this. Right, and so we know we can come down. So from here, that means that we're going to come down to our low, and we're going to come back up to our high. So we see this. So if we think of the entire sine function, well, no, it does not pass the horizontal line test. So it is not a one-to-one function. Therefore, it does not have a inverse. However, if the domain is restricted to a certain interval, it can have a inverse within an interval. So if I want to look at sine, and let's look at only in this interval, right? Now if I look at it's only during this space here, notice that I can draw horizontal lines here, and we are passing those horizontal line tests. So therefore, we do have an inverse here because it passes both the horizontal line test and the vertical line test. So we have a function and a one-to-one function. So coming back over here, right, the inverse of sine function is what we call the arc sine function. The inverse of cosine function is the arc cosine function. The inverse of tangent is the arctangent function. All right, let me come back to our function here. So thinking of sine, we've restricted it to only look between pi over 2, negative pi over 2 to pi over 2. So that means that our domain is that specific interval. So we are going to equal pi over 2. So it's going to be a closed interval from negative pi over 2 to positive pi over 2. Our range then, our minimum is going to go from negative 1 to 1. Okay, so that is the parent function we're looking at. So now what happens when we look at the inverse function? So one thing we know about inverses is that the domains and the ranges swap. So then that means that my domain for my arc cosine is going to go from negative 1 to 1. And my range for my arc cosine is now going to go from negative pi over 2 to pi over 2. Okay, so notice how the axes here has changed too. Notice I have pi over 2, negative pi over 2, and now I'm looking at 1 and 1. Okay, so what does this function look like now? So let's start by looking at some of these points. So we do have negative pi over 2, negative 1 here. And so if we graph that over here in our inverse, swapping our x and our y's, we're going to be graphing at negative 1 and pi over 2. If we graph the origin, 0, 0, that's going to be graphed as 0, 0. And negative and positive pi over 2, 1 is going to be graphed over here as 1 of pi over 2. Now, looking at this, it does look like we have those same exact points. So therefore, our graph is going to be very similar. But if we remember, we do have inverses must reflect about the y equals x axis. So where our inflections for this sign should have, followed something like this curvature, the concavity, right? So we have a concave down and then a concave up. So these are going to be swapped. So now we're going to kind of come up this way and down this way. Okay. So you can kind of think of all of those pairs are going to be swapped out. So we argue that concavity is going to change with the arc sine function. All right, let's take a look at the next function here. We're looking at arc cosine. And so similarly to arc sine, we're going to be taking a look at the cosine function first. So noting that we are restricting the domain of cosine to 0 and pi. And so thinking about that, that means that our domain is going to be restricted from 0 to pi. So what is that going to look like? That's going to look like at 0, when we plug in 0 for x, we are going to get an output of 1. So we have the value 0, 1. Right? When I plug in pi to cosine, we are at 0. So we're going to get the value pi, 0. Okay. And now we can plug in the value, oh wait, sorry. At pi, I'm thinking sine. At pi, we're actually equal to -1, right? So we should not be at pi. We should be at right here, pi -1. And then at pi over 2, this is where our cosine would equal 0. So we get pi over 2, 0. And so thinking about what does that concavity look like? So the concavity of our cosine function is going to kind of look like this. It's going to swerve downward and come back like this. Right, so we have kind of like a S-looking shape, right? So our range is going to go from, just like our sine function, going to go from our minimum, which is -1, to a +1. So now that we look at our arc cosine, first thing we need to know is that our domain is going to be the range of the original function, and now the range is going to be the domain of the original function. So we see this particular graph. All right, so that means that we can flip all of these. So I'm going to have at 1, I'm going to be at 0. At pi over 2, I'm going to have x equals 0. So I'm going to have 0 pi over 2. Here I'm going to have 1, 0. And then lastly, at -1, I'm going to be at pi. So you can see all those values have swapped here. And so because of that reflection that we talked about earlier, the concavities are also going to switch. So from left to right, we're going to kind of look at a concave down and then looking towards a concave up. So here's that function. So we can see how those concavities have swapped there. Finishing out our 3 trigonometric functions, we are going to be looking at arctangent. So arctangent, notice that we are going to restrict that domain to -pi/2 to pi/2. So that's going to be our domain. And actually notice that we won't be including it, because if you recall the tangent function, at -pi/2 and pi/2, we have asymptotes. So let's go ahead and graph those asymptotes here. Right. So that means that for our arctangent, we are going to be seeing a range go from -pi/2 to pi/2. And so looking here, right, recall that our tangent function, right, at 0, right, so tangent of 0 is going to give us 0. So we are at the origin, right? But also recall that if we have tangent of pi/4, that equals 1, because that's when we get square root of 2 over 2 over square root of 2 over 2. So we are at +1. And so if we think of tangent of -pi/4, right, we would have -1. And so we'd have -1 because if you recall, we were going to be in the fourth quadrant, and the only thing that's positive there is cosine. So we would be at -1, so we'd have these values here. Oops. So our tangent function does go off into infinity, right? And looks like this, right? And we are going to kind of start curving towards getting close to those asymptotes there. So what's the range? Well, our range is going to go from -infinity to infinity. Keep in mind that when we talk about a range or a domain of infinity, this should always be open because infinity is a concept. It's not a destination, so we can't really ever equal infinity here. So that means that the domain for the arctangent function is going to be -infinity to infinity. So we can see how all of this kind of swaps out. So taking a look at this, we are going to be, we're going to have a value of, so let's write these down actually. So this is 0, 0. Here we're going to be at pi/4, 1. And here's going to be pi/4, negative pi over 4, negative 1. So now we're going to see that replication here. So at negative 1, we are going to be at negative pi over 4, which is going to be right here. So this is negative 1 comma negative pi over 4. At 0, 0, we're going to be there. And then at 1, we are going to be at positive pi over 4. So just like tangent has those vertical asymptotes, cotangent is going to have some horizontal asymptotes here that we're going to kind of see. And so our function is actually going to be the reflection of the tangent function. So if we kind of picture, let's see if I can change this color here. So if we picture this line here and think of what that reflection would look like about that line, right? We'll see that we'll get something that looks like this. Okay. And so there's our graph for our arctangent. All right, so let's go ahead and continue. We're going to start talking about evaluating inverse functions. So we're going to use the unit circle to help evaluate the inverse trigonometric functions. However, remember that the domain and range are restricted in trigonometric functions. So we do kind of keep those domain and ranges in mind. So we want to find the exact values of each expression if it exists. So first and foremost, let's look at the first one. So arc sine of 1. This is telling me that sine of some value equals 1. So what can that value be? So if we look at our inverse function, our unit circle, sorry, remember our sine value, right? So our sine of theta is going to equal y. So I can see that y equals 1 here, right? And so in this particular case, I know that the answer is going to be either 90 degrees or pi over 2. So this is going to end up being pi over 2. Right? Take a moment and try number 2. All right, so hopefully for number 2, you got pi over 3. Just coming back and looking at the unit circle, right? So when does sine equal root 3 over 2, right? Is that pi over 3? Now, for the next question here, it is asking us, well, arc sine of negative 2, right? So this is telling us that if I take sine of theta, when does it equal negative 2? Well, keep in mind, what is the domain and range of sine of theta? And what is the domain of arcsine? So the domain of arcsine is going to go from anywhere from negative 1 to 1. 2 is outside of that domain, so therefore it does not exist here. Okay. All right, take a moment and try 4 through 9, keeping in mind that when we look at cosine of negative 1, this is the same thing as saying arc cosine of that theta. Okay, so go ahead and try 4 through 9. All right, let's take a look and see if we're in agreement here. So for number 4, we should have 3 pi over 4. For number 5, 3 is not within the domain of that inverse cosine, so it does not exist. For number 6, we should have the answer of pi. For number 7, the correct answer would be pi over 6. For number 8, it should actually be negative pi over 4. And number 9 is pi over 3. So let's just kind of look over at the unit circle real quick and kind of discuss why this one would be negative pi over 4. So when we're looking at the unit circle here, we got to keep in mind that the domain of our sine of theta is going to go from pi over 2, from negative pi over 2 to pi over 2. And so when we look at, this is where we are restricting the function of sine of theta so that it can in fact be a function that is 1 to 1. So that means that when we're using the unit circle, we're really using this half of the circle. Okay, we are going from negative pi over 2 all the way through pi over 2. So when we look at these values and then going back to the problem we were just looking at, we're looking at when does arctangent equal negative 1. So arctangent is going to equal negative 1 here, okay, because this is when we get that y over x. Sorry, it doesn't equal, not there, class, sorry. at our pi over 4 here, because this is where we're going to get that y over x, and we're going to get that negative 2 pi over 2 over that 2 pi over 2, which is going to give us that negative 1. So it's happening here. So we really want to kind of keep in mind, right, that we are looking at, for sine and tangent, actually, I should say, specifically, for sine and tangent, we are looking at these two quadrants. When it comes to looking at cotangent, let's see if I can change this color. When we're looking at cotangent, we're really looking at from 0, sorry, not cotangent. When we're looking at cosine, we are looking at this half of the circle, right? Because we need to incorporate when cosine will equal those negative values. So cosine of theta, that's why the cosine of theta domain is going to go from 0 to pi. And so cosine, we're looking at quadrants 1 and 2. And then for sine and tangent, we're looking at quadrants 1 and 4. Okay. All right, so hopefully that helps in trying to identify, right, what is the angle that we're looking at. And when we're looking at quadrant 4, we're usually using those angles in the negatives and not the 5 pi over 3s and stuff like that. We're going to be looking at that as negative pi over 3. All right, come backing over here. Let's take a look at some of these application problems here, 10 through 12. So for number 10, we have a ship left port A and sailed 60 miles due east to port B. From port B, the ship sailed 120 miles northwest and stopped at a position directly north of port A. From the beginning of port B to the current location, we want to find the bearings, sorry, from port B to the current location of the ship. All right, so let's start off by drawing a picture here. So we're looking at port A. So here's my port A. And actually, let me come back over here. Here's my port A. And we are going 60 miles due east. So this is our 60 miles due east to port B. And then from port B, we sailed 120 miles northwest. So northwest is going to come this way. Okay. And so this is going to be 120 miles traveled. And so the question here, though, is we want to find the bearings at port B. So remember, when we're looking at bearings, we're looking up against the vertical, the north to south axes, right? So that's what we want to know. We want to know, what is this angle here? So in order to calculate this angle here, let's call this theta 1, we really need to know, okay, what's going on here? So let's calculate this angle, right? And so that angle, looking at this, is going to be, because I have my adjacent and my hypotenuse, right? I know that cosine of theta is going to equal 60 over 120, which tells me that I have arc cosine of 60 over 120 is equal to my theta, right? So I'm just implying that inverse, which we've already been doing. And so in doing this, let's come over here to our calculator, and I'm going to come over here to functions. Here's my cosine inverse, or my arc cosine, and I have 60 divided by 120. All right, we hit enter, and we see we get those 60 degrees. So this is going to be theta equals 60 degrees. So our 60 degrees is here. It's this original theta, but I want to know, well, what is this? So keeping in mind, right, that we are making a right angle here, this means that we are going to take those 90 degrees from our right angle, and we are going to subtract the 60 degrees of our theta just to calculate our theta 1. And so we see that we have 30 degrees. So that means that our bearings are going to be, because we're going north and west, we're going to have north 30 degrees, west are going to be our bearings for this particular problem. Okay. All right. So hopefully that made good sense. Let's look at number 11 here. The angle of elevation from the football field to the crossbar and the goalpost depends on D. So we see here, we have this image, and we can see that this angle, our theta, depends upon this D. So it says write theta as a function of d. So when we write theta as a function of d, this is really telling us, well, theta equals something and there's d somewhere in that function. That's what that means. So let's take a look at this. So I know that I have 10 feet here. I have my d and I have my theta. So because I'm looking at adjacent and opposite, this tells me I'm going to be using the function tangent of theta is equal to my opposite 10 over d. Now, this is a function that helps us find theta, but because I want to write theta as a function, again, I want to have it as theta equals. So this is a key that I should have theta equals something. So what am I going to do? Well, I'm going to take the arctangent or tangent inverse of this. And so I'm going to end up with theta equals arctan of 10 over d. And that's going to be our function here. And so using your graphing calculator, find theta when d is equal to 75 feet, round to the nearest tenth of a degree. So we're going to use Desmos calculator for this. You can use your scientific calculator if you'd like. We're going to come over here to functions. We're going to do tangent inverse, come back to the main function here. And this time we're going to do 10 divided by that 75. And so we see that our answer is 7.59. So coming back over here, this tells me that theta is equal to arc tangent of 10 over 75, because I'm just replacing that 75 for that d. And then this is going to give me that 7.6 degrees based off of our calculator. All right, take a moment and try number 12. All right, number 12 is a little bit trickier. So we're looking at two cables are secured from the top of a 50-foot utility pole. So we see the 50 feet here. And then we want to be able to we want to write theta as a function of c and 1. So again, we want to start off with that theta equals something. So notice that if we take arc cosine of 50 over c1, that's going to give us this entire angle here, right? Because cosine, remember, we're using this right triangle here. Cosine of this entire angle is going to be our adjacent over our hypotenuse, which is going to be that 50 over, and the 120 comes in part 2, but over that C1. But that's going to give us this entire angle here. That's not exactly what we want. We want just theta. So we need to be able to look at this smaller triangle here. Let's see if I can highlight this. There it goes. This smaller triangle here and remove that angle. And so when we're looking, we want to get rid of this little piece of this angle here. And so what is that angle, right? So that angle in gray is going to come from, again, another cosine, but this time we're going to do 50 feet over C2. So that's what we're subtracting over here. And so that's how we get that entire angle theta. Now, using the graphing calculator, we're going to use Desmos calculator. If you don't have a graphing or scientific calculator, we want to find theta if the larger cable is 120 feet, and then we have 65 feet. So our C2 is going to be 65, and our C1 is going to be 120. And so we see here is our equation. So when you plug that in, you should get an angle of 25.7 degrees. All right, hopefully all of this is coming together. That's the end of this video.